The internet is awash with viral clips that freeze your blood. An airliner, like a stumbling giant, tilts onto its side, its wingtip threatening to scrape the tarmac, while the camera shakes from the fury of the crosswind. Commentators, hearts in their throats, type, "It's going to crash," and "It's about to cartwheel." It's spectacular. It's terrifying. And it's almost always a trick of the light. Our brains, those masterful creators of catastrophe from nothing, whisper a simple primal warning. If a vehicle leans this far, the next step is a rollover. This fear is ancient and instinctual, like the fear of falling. It's born from everyday logic. A strong gust equals a fall. But an airplane operates under a different, non-negotiable set of rules. That dramatic tilt, which from the outside looks like a death throw, from inside the cockpit often feels like a complex yet routine piece of work. One pilot, watching such footage, once remarked, "It's like watching surgery from the outside. For the uninitiated, it's bloody chaos. But for the surgeon, it's a precise sequence of incisions." The passenger sees a near disaster. The pilot sees a bank angle of 5 to 8 degrees, easily countered by the ailerons, and a lateral slide being nullified by a deft combination of rudder and control inputs. So where's the trick? In the conflict between visual drama and the cold, hard math of aerodynamics. Our eyes fixate on the fuselage's sharp angle relative to the horizon. But for the aircraft, that horizon isn't the line of the runway. It's the relative wind, the oncoming flow of air. Pilots aren't landing on a flat asphalt, but on an aerial road, aligning the machine with the wind. A strong crosswind forces them to present the wing into the airflow to generate necessary lift, while the fuselage ends up angled away from the runway. This isn't a failure, it's a controlled and deliberate maneuver called a crabbed approach or a side slip. And just as the viewer braces for the sickening crunch of shearing metal, engineers know the truth. The landing gear is built to withstand not just a vertical impact, but colossal lateral loads, calculated and tested to extremes far beyond what most storms can muster. The crew has trained for worse in simulators, practicing the crosswind correction, the moment the plane straightens out moments before touchdown. This isn't Russian roulette. It's the pinnacle of piloting skill, a ballet where every element, from flap management to touching down on one wheel first, is a rehearsed and precise movement. The real danger isn't flipping over. Achieving that would require angles of attack and bank that are physically almost impossible near the ground. The real risk lies in veering off the runway, in a loss of directional control during the rollout. But that's not nearly as cinematic, and so it almost always stays behind the scenes. The image that forms in a passenger's mind when they see an airliner tilting on its wing in a gusty crosswind is pure Hollywood blockbuster. The brain conjures an apocalyptic scene, a steel behemoth caught by the invisible hand of the storm, flipping onto its back with a deafening roar. The reality is far more mundane, and upon closer inspection, utterly brilliant. An airplane isn't a sailboat, it's an aerodynamic chameleon whose life depends on its ability to negotiate with the air. The crosswind, that invisible adversary, doesn't attack head-on but at an angle. Its primary goal isn't to flip the plane, but to shove it sideways. This is where engineering sorcery takes over. The fuselage isn't just a tube with seats. It's a carefully sculpted cigar. Its contour is designed to slice through the flow, forcing the wind to wrap around the body rather than punch a single point. The pressure distributes itself over a vast area, from the nose to the tail, transforming a concentrated blow into a diffuse, almost gentle caress. The wings act as giant stabilizers. Their surface area and elasticity dampen the energy of the gusts, much like a trampoline absorbs the force of a jump. The numbers here are the best antidepressant for anyone with a fear of flying. The engineers, those glorious nerds with their slide rules, have crunched them all.
To make a mid-range Boeing or Airbus even begin to lose its balance on the ground, it would require a wind comparable to a Category 3 hurricane, a steady, relentless 110 to 125 miles per hour. That's the kind of wind that tears houses from their foundations, not one that merely rattles the beverage cart. The actual operational limits at airports are far more modest. Even on the bumpiest, most nerve-wracking flight, pilots are dealing with crosswinds in the 30 to 40 mile per hour range. The gap between these figures is that all-important safety margin that lets engineers sleep soundly at night. So, what are we seeing from the window? Why does the plane look crooked right before touchdown, as if it's slammed into an invisible wall? This isn't a sign of a struggle. It's high-level piloting, a technique called the crab. The pilot intentionally yaws the aircraft, pointing its nose into the wind, presenting its forehead to the gale, while the plane's body continues to track down the runway centerline. It's the aerial equivalent of a crab walking sideways. In the final seconds before contact, the pilot executes a swift, decisive kick of the rudder to straighten the nose and align the wheels perfectly with the centerline. That sharp, almost jarring movement isn't a mistake. It's a feat of precision, akin to a Formula One driver's last-minute steering input before a tight corner. There's another silent ally in this dance, the airframe itself. It's not a rigid monolith. When a sudden gust hits, the long wings flex and bend slightly, acting like flexible spring absorbers. This aero-elasticity is a passive yet powerful safety system that absorbs and dissipates the very kinetic energy a passenger's imagination would use to flip the plane.
You might think a crosswind for an airplane is like a nudge in the side for a pedestrian. Take a step to the side, and you're fine. But at 150 miles per hour, that analogy shatters. The physics here are playing a different game, a brutal one, with three forces forming a clandestine alliance against the pilot. The first force is the wind itself. It doesn't just push, it tries to spin the plane around its vertical axis, like a top. The second force is inertia. A 70-ton metal behemoth doesn't want to change direction just because the wind blows. It wants to keep going where it was pointed. And the third force is friction. The landing gear, which at this moment hasn't yet touched the ground, is about to become the point where theory meets harsh reality. This is the stage for the main event, the showdown with an invisible opponent. Pilots don't fight the wind head-on, they trick it. Or, in the language of physics, they create a system of counterforces that turns chaotic drift into a controlled, predictable movement. The most visual trick is the crab. The airplane approaches the runway not straight, but at an angle. The nose points into the wind, like a bird side-eyeing the branch it's about to land on. From the outside, it looks like the airliner has decided to land sideways, but it's an illusion. The pilot deliberately yaws the plane, using the wind as an ally. The vector of the plane's own speed and the vector of the wind speed add up. As a result, relative to the ground, the machine moves right down the center line, even if its nose is pointed toward the hangars. It's genius and paradoxical. To fly straight, you have to fly sideways. But here lies the main trap. Touching down in this crabbed posture is a sure path to disaster. The landing gear isn't built to handle giant lateral loads. It's like tripping at a full sprint. Your ankles would give way. So, just dozens of meters above the ground, the pilot executes a second, even more subtle maneuver. He kicks out the crab, aligning the plane with the runway centerline.
This is where the wing-low technique comes into play. This is no longer a course adjustment like the crab, but a work of jewelry. The pilot banks the plane slightly, lowering the wing on the side from which the wind is blowing. The leeward wing ends up slightly lower than the windward one. This creates a counterforce that stops the wind from pushing the plane sideways. Simultaneously, the pilot uses the rudder pedals to keep the nose pointed straight down the runway. The plane screws itself onto the pavement, creating the perfect orientation for touchdown. Why is this dance of bank and slip so effective? It's all in the aerodynamics. The lowered wing has a greater angle of attack and generates a bit more lift. It's this force that counteracts the drifting push of the wind. The result is a self-compensating system. The stronger the wind, the more bank and slip angle are needed to neutralize it. Experienced pilots feel this connection on a muscular level, like a biker feeling the road in a turn. In particularly nasty conditions, when the wind isn't just strong but savagely gusty, the script can get even more dramatic. Pilots may make an approach planning for the initial contact to be on one main gear, the leeward one. It's like a motorcyclist putting a foot down in a sharp turn. It allows the aircraft to hook the runway, stabilize itself, and only then gently lower the other gear. In Boeing manuals, this is described in dry prose, but between the lines, you can read a real challenge. Requires timely correction. Timely here isn't about seconds. It's about the tenths of a second that separate mastery from an emergency. All of this complex mechanics isn't just a set of technical skills. It's a dialogue with physics, where the pilot, using its own laws, persuades the elements to play by his rules. He doesn't defeat the wind. He negotiates with it to perform together one of the most beautiful and precise procedures in all of aviation.
The first protector is hidden in the very shape of the wing. Look at an airliner on the tarmac. Its wings aren't just sticks poking out of the fuselage. They form a subtle V with the body. This is dihedral, that clever angle that turns a problem into a solution. Its mechanics are pure poetry of counterbalance. Let's say a gust hits from the left and tries to lift the left wing. In that instant, the plane starts to bank to the right. And this is where dihedral performs its signature trick. The right, now lowered wing, meets the oncoming airflow at a greater angle of attack. For a wing, this is like an adrenaline shot. Its lift instantly surges. Meanwhile, the left, raised wing does the opposite. Its angle of attack decreases, and it relaxes, losing lifting force. An imbalance arises, but not a fatal one, a saving one. The low wing pulls up. The high wing doesn't resist. The plane gets a gentle but authoritative nudge back to level flight. That wasn't the pilot reacting quickly. That was nature's built-in autopilot, an engineering genius coded into the wing's geometry. On some jets, this angle can reach up to 6 degrees, as if they're perpetually primed to counterpunch any wind. But a single line of defense is unreliable. While the wing parries one threat, the wind can attack from another flank. And here enters the second guardian, the vertical stabilizer, the fin. That giant tail fin isn't just the rudder many think it is. In reality, it's the aircraft's anchor in the aerial ocean.
When wind presses from the side, it doesn't just try to roll the plane, it also tries to turn it, to present its side to the flow, into the deadly posture of a side slip. This is a lethal stance. But the vertical stabilizer resists. Its surface area is massive, and the wind pressure on it creates a powerful moment that seeks to swing the nose back into the wind. It's like a sailboat. The deeper and bigger the keel, the harder it is to capsize with a wave. Yet even the most perfect wings and fins are nothing without the third main guardian, the center of gravity, CG. Its location is the holy grail for load planners, checked with sacred rigor before every flight, recalculating with the weight of tons of baggage, passengers, and fuel. This whole colossus must be perfectly balanced around a magic point. If the center of gravity is low and centered, the plane becomes a clumsy but incredibly stable top. Any gust trying to tip it over must fight not only aerodynamics, but also the inertia of all that mass, which desperately resists being overturned. It's pure physics. The lower and more central the weight, the harder it is to upset the object's equilibrium. As one engineer put it, proper weight and balance is like a plus 15% bonus to the wind resistance stat, a number behind which lies the calm of passengers in their seats. So this is how the trio works in concert. The wind attacks. The wing's dihedral parries the first blow, creating a correcting force. The vertical stabilizer dampens the yawing motion, holding the course. And the low center of gravity gives the whole structure the inertial stability of a heavyweight. They don't just protect, they transform a chaotic blow from the elements into a predictable, manageable event, one that the automation and pilots can handle with a couple of gentle control inputs.
The landing gear isn't just wheels on struts. It's a complex anti-tipping system, the aircraft's personal bodyguard on the ground. Its work against the wind is built on 3 pillars: width, flexibility, and intelligence. Take a heavy figurine on a narrow stand. It's easy to knock over. Now place it on a wide, massive pedestal. That's roughly how the main landing gear works. The wider the base, the distance between them, the higher the stability moment. It's a fundamental law of physics. On giants like the Boeing 747, the base of the main landing gear bogies exceeds 12 meters. That's the width of a small house. Imagine this winged mansion racing down the runway. The wind strikes the flank, but toppling this behemoth is as difficult for it as knocking over a tightly packed rugby scrum. The lateral load from a gust is distributed immediately across all wheels of the giant bogie, not just a single one, turning a point impact into a managed pressure that's dampened by the structure. But width alone isn't enough. What if the wind strikes precisely at the moment of touchdown, when the wheel is already on the tarmac, but the strut hasn't yet settled into a stable position? This is where special mechanisms come into play. Energy absorbers. These aren't just simple shock absorbers like in a car. They are high-tech buffers capable of dissipating kinetic energy not only vertically, but also horizontally. When the first touch happens at an angle with a lateral skid, these devices take the hit, preventing the sharp load from transferring into the wing and fuselage. Some systems go even further. They're equipped with intelligent mechanisms that within milliseconds slightly turn the wheels into the wind. Yes, it's counterintuitive, but this is how they soften the moment of contact and reduce the tipping moment. As one experienced engineer noted, modern landing gear is calculated to absorb not only the vertical load, but a significant lateral moment. Otherwise, no landing in crosswind conditions would be possible.
A crosswind to a pilot isn't some abstract number on a weather report. It's a constant, shoving shoulder, trying to weather vane the plane like a sailboat. Pilots aren't dervishes. They don't wrestle the wind hand to hand. Their primary weapon is a cunning maneuver known as a side slip or a D-crab. The jet is lined up with the runway at an angle, its nose pointed into the wind. In the final seconds before touchdown, the pilot swiftly kicks it straight, literally slicing off the lateral drift. It's a work of precision. But what happens when this delicate dance is disrupted? Imagine you're driving on an icy road and a sudden gust slams into your side, now at a speed of 250 kilometers per hour and several hundred tons of mass. The force is immense, yet it's rarely the sole culprit. It's always a perfect storm of circumstances. Take the case of the Bombardier CRJ-900LR in Toronto, February 2025. The aircraft was landing on a snow-covered runway with a crosswind of about 50 kilometers per hour. Doesn't sound that terrifying, right? But the key is in the word snow-covered. The landing gear lost traction with the surface. The plane became an unguided sled. Deprived of its grip, it couldn't fight the wind, veered off the runway, and its own inertia finished the job, rather radically by flipping it onto its back. As one expert aptly noted, an airplane on a jet flipping over is quite rare. It's the aviation equivalent of winning the anti-lottery. Another telling incident is the Fokker 50 in Mogadishu in 2022. The plane tilted and overturned, but of the 36 people on board, only 3 were injured. This case is a powerful testament to the resilience of modern aircraft. The cabin remained intact, and passive safety systems did their job. Even in such an extreme situation, the design worked as planned. There are also less dramatic but no less unnerving scenarios where a plane's wingtip scrapes the runway. It's a sight that stops the heart of any aviation enthusiast. But this is where the engineer's built-in safety margins kick in. Wingtips aren't made of crystal. They're designed to withstand monstrous loads. Often, it's this very robustness combined with special landing gear that dampens the roll, which allows the machine to stay on its feet, recovering from that excessive bank. A myth that needs dispelling once and for all. An airliner won't flip from a single gust of wind. It takes a whole conveyor belt of misfortunes, a slick runway, a loss of traction, a sudden squall, and possibly a technical failure. Statistically, the probability of such a chain of events is vanishingly small, fractions of a percent. Aviation is built on paranoia, and every one of these stories is picked apart piece by piece to make flying even safer.